You've probably heard me say this more than a few times over the course of this journey. Over the past 17 or so episodes, we've been building a pretty cool circuit. It's an LED driver circuit, not just any driver circuit, but it's a driver circuit that you can control the intensity and it doesn't use pulse width modulation. The promise that I've made is that we're going to clean up the monstrosity of mess that we've created. So today, we're going to take the first steps of turning this beautiful yet terrible spaghetti of wires into something like this, a custom printed circuit board. So to do this, we can do it a number of ways. We can basically take this entire circuit that we have here right now and convert it into a printed circuit board. And although we could do that, I want to put some thought into how we're going to do that because I think we can be a little bit more streamlined as we think about our design as we go forward. Well, let's take a look at what we have here. This portion in the top left over here, this is it's basically a clock generator portion, but it also has two buttons. And those two buttons allow us to turn the intensity of the LEDs higher or lower. Down here, we have an alternative user interface. This uses a rotary encoder or a dial that I can turn so that the intensity of the LEDs goes higher or lower. On the middle breadboard is all of our logic that we needed to use so that the LED intensity doesn't go beyond the maximum or below the minimum, and it has all sorts of stuff to make sure that it can increment at a comfortable pace. And on the right side, on the top over here, we have the actual driver circuit, which takes the signals generated from this logic center over here and drives the actual LEDs according to a proper intensity level, basically controlling the current. And down here, we have another optional component, or a optional component, that will give us an intensity indicator. So when our LEDs are low intensity, the light down here will illuminate. And as we increase the intensity, it goes all the way to the maximum up there. Those are a lot of components. And like I said, we can cram them all into one board, but I think we can do better. Every single time we make one of these, we're going to need the logic in the middle. Without that, this system doesn't work. There is an option, though, of user interface. So we're not going to need both of these circuits. We're going to need one of them. We're either going to choose to implement the button interface, or we're going to choose to implement the dial interface. On the bottom right, we have an indicator LED, which we may or may not choose to implement. So this is entirely optional. And the drivers at the top right, the drivers that we have right now will control a single set, in this case, 3 LEDs, high power LEDs, that run on 12 volts and can range between 0 and 350 milliamps. That's what we've created here. But the way we've designed it is we can actually daisy chain a number of these drivers together so we can control more LEDs. They're all going to be at the same intensity, of course, but this is really neat. And we're only limited by maybe the physical characteristics, so how big this board is going to be. We're also limited by the current handling capacity. So of course, this could be, with one driver, we have a maximum of 350 milliamps. With 2 drivers, we'd be at a maximum of 700 milliamps. And you can see how it goes up. And we're going to reach a limit, of course, because we really can't surpass some of the current handling capabilities of our circuit. But this means that we can be a little bit flexible with our design. So let's diagram this out, shall we? At the center of it all, we're definitely going to have our logic. And we're going to need to choose a user interface. It's either going to be the button interfaces, or it's going to be the rotary encoder or dial interface. And at the other end of the logic, we have our drivers. And as we just discussed, we can we can add a number of drivers in parallel so that we can get more light output with the same logic circuit. And finally, we have our indicator LEDs, which we can either include or not include. So one of the ways we can approach this is we can take each and every one of these boxes and create a separate printed circuit board for each one. And we can do that, and we can mix and match the boards as we please. So that's definitely one way to go. But I want to keep this a bit simple, So maybe one of the things I'd like to do is maybe we can create a single circuit board or single printed circuit board that will accommodate most of these items, but will only implement the ones that we want. So it's kind of like the board will be a canvas and there's always going to be blank areas. It's going to look like there are chips missing, but that's okay. We've designed it so that it can do that. I'd like to take that approach. That way we can minimize the number of boards that we need to build. However, I think perhaps this will sit on its own board. So that way, if we can add as many of those as we like, but, like I said before, limited by our physical space or limited by our current handling capabilities, but the rest of it will sit on a single PCB. So how do we get started designing one of these things? I mean, they look pretty complex, don't they? But at its heart, it's actually pretty simple. This is basically just a two-sided board. There's circuit on one side and circuit on the other side. And essentially, the only thing it contains is a bunch of pads and traces. The traces are equivalent to the wires that connect our circuit, and the pads are where the components plug in. And in this particular board, you'll actually be able to see some pads are through hole, which means it goes through the board and shows up on the other side. And some of the pads are what we call surface mount pads, meaning they just sit on the top and don't go through the other side. Now, the surface mount components are they're more modern. They're the way that most modern circuits are designed, but they're also harder to use. They are incredibly tiny. We'll graduate there. I think for now what we'll do is we'll keep things very simple and we'll design our printed circuit board with through-hole components only. So that's going to have the advantage that's going to be easier for us to build. It's going to have the disadvantage that it's going to take up more board space. So the board is going to be a little bit bigger. But like I said, let's give it a shot. Let's take a closer look at the board and see how we actually make one of these things. All right, so there we have it. Now, this board that you see on the screen, this is not the same circuit that we've designed so far. It can't be. We haven't even designed or built it yet. This PCB is actually from a previous design that I had made for something entirely different. But I wanted to use it because I want to go through the details of how we go from a physical breadboard design, the wiring that you saw earlier, to this. You can clearly see where the traces are. So you see the dark green background, and then you see the lighter green shade where you see these lines kind of coming in. Those are the traces, and those are the equivalent to the wires that we have. So these connect all of the different pads that you see on the circuit board. So the pads are typically outlined in white, but within those the white areas, you can see every single one has at least two of these metallic pads, and those two metallic pads are where the component sits. So if you look at these things that I'm pointing at right now, these happen to be resistors, and a resistor has two prongs, and those prongs go through these holes and get soldered into the PCB. Some components have more than two, like this one over here. This is a transistor or a MOSFET, I'm not exactly sure, but it's got three prongs, and those three prongs go in and get soldered in. Some have even more. I think this one I think this was a relay if I'm not mistaken, but it's got about 8 prongs. So basically, we have the total freedom to design the board as we see fit. We can locate all of the different components on the board wherever we think it's necessary and connect them with the traces. There's a few things we got to keep in mind. Every board has multiple layers. In the most simplest of the boards, especially the one that we're going to create, has 2 layers. So we have a layer on top and a layer on the bottom. And if you look closely at all of these different traces, notice none of them cross. And that's important. You can't cross a trace with another trace on the same layer of the board. If you need to cross it, you've got to make the trace go to the other side of the board so it can cross over. Each and every one of these through-hole pads has a hole that's drilled straight through. So every through-hole pad exists on every layer. And that's useful. That gives you a bridge that you can actually take a signal from the top layer and move it to the bottom layer. All right. Now, how big do these holes have to be? And how big do these traces have to be? Well, let's start with the traces because they're actually pretty straightforward. When it comes to choosing a manufacturer for the printed circuit boards, they always have limitations. Different manufacturers will have different limitations. So, for example, the manufacturer that I'm going to use for our circuit board says that these traces over here, they have a minimum thickness of 0.15 millimeters. They can't print anything smaller than that. They also say that the minimum spacing between these traces or neighboring traces has to be 0.15 millimeters. So anything closer than that, and they're not going to print. Their manufacturing capability cannot exceed that. Different manufacturers will give you different capabilities. So as far as these traces are concerned, just to keep the numbers simple and easy to design, I keep the traces. I don't know what these ones in particular are, but the board that we're going to make, we're going to keep the traces at 0.2 millimeters, unless we need to push a lot of current. And when we need to push more current, we're going to increase the size of that trace. Now, how much do we increase it by? Actually, it's not that difficult. If you just Google PCB trace width calculator online, there's tons of tools available that you can actually punch in how much current's going to go through, the amount of temperature rise that you're comfortable with, and it'll spit out the thickness of the trace that you need to apply. So there's lots of tools available to calculate how thick those traces need to be. We won't get into the details, but just know this. If you're going to push more than a minimum amount of signal current, do the calculation and figure out what a safe trace thickness is going to be. So that part, pretty straightforward. Let's get into the more nitty-gritty bit here and let's talk about these through-hole pads. All right, so these through-hole pads have a lot of requirements. First of all, you have to make sure that the device that you're sticking in there will fit. So in order to do that, take a look at the data sheets. So for example, here's a data sheet that I have up on the screen right now. There we go. This is a data sheet of the capacitors, some of the capacitors that I've been using. And if you scroll down in the data sheet, you'll find what you need. Oftentimes it's buried at the end. I saw this and I thought, oh, it's going to be in here somewhere. It actually wasn't. I had to scroll down a little bit more. And if you keep going past all this stuff, you'll get to this. And over here, it actually says to you, all of these little leads, the leads that come off the capacitor, look at this. It tells you that the thickness of those leads or diameter of those leads is noted by this lowercase d. And if you go down to the table, it'll tell you that the lowercase d is the wire lead diameter and it's 0.5 millimeters with a variance of 0.05 millimeters. Here's another data sheet of an IC that we're using. This is a 4049 IC. And if you look at this, you can actually see that these leads are square. They're not round, they're square. So one dimension of those leads says that it's 0.25 millimeters thick. Another dimension right down here says that this is 0.53 millimeters thick. So that's actually not a square, it's a rectangle. And so when you have a rectangular lead, make sure you calculate the diagonal across that rectangular. So it's a very simple calculation. In this case, it turned out to be 0.25 squared plus 0.53 squared, and then you take the square root. So hypotenuse, triangle, trigonometry, think back. And when you get that number, for this, it turned out to be 0.58, I think it was. 0.58 was the maximum lead diameter of this particular lead. So just round it up to 0.6 millimeters. That's for this. Some data sheets will make it even easier for you, and they'll tell you right away, oh, sorry, this one is sideways. Let me fix that for you. Much better. Okay, so some data sheets will actually even tell you what the layout or the recommended PCB layout is. See, so this one tells you right here, PCB layout. Here are the hole patterns that you want to put in, and it tells you right here that the diameter of the hole itself needs to be 0.8 millimeters. That's not the lead diameter, that's the hole diameter. So take a look at the data sheets and you'll find the answers you're looking for. Sometimes you won't. And in that situation, it's probably good to get yourself one of these. This is a digital caliper. They're fantastic. They're not very expensive. Well, I mean, I guess you can spend a lot of money on it, but they're not too expensive at all. And it's really neat because it'll allow you to take the leads, stick them between those two prongs, and get a very accurate measurement as to how thick or what the diameter of those leads are. It tells you right there. This one, 0.47 millimeters. Perfect. Handy tool. Get yourself one of these. But you can't stop there. When the PCB manufacturer drills those holes, there's always going to be a bit of a variance. take a look at the capabilities of your manufacturer to find out what that variance is. For our particular manufacturer, the variance, I think it was 0.08 millimeters or something like that. So it could be like if you ask for a hole that's 0.5 millimeters, it might be as small as 0.42 or as big as 0.58. So there's a variance there, and you've got to take that into consideration. But that's not all. Take a close look at this PCB and take a close look at some of these holes. Let's choose this one over here where my pencil is. See how there's a hole in there and you can kind of see through it, but look immediately outside that hole. There's a little ring of metal. And that ring of metal is very important because that ring, first of all, gives us connectivity, electrical connectivity to the device, but it also allows us to anchor the device. We're going to solder these things in. You need to have a ring of sufficient thickness around every single hole. So we call it the annular ring. How thick does that annular ring need to be? Well, the standard gives some advice, and I'm sure if you Google it, how thick does through-hole component annular rings need to be? One of the more common things that I've seen is that doubling. So if your hole is 0.5, then the annular ring should be double that, or 1 millimeter. If your hole is 0.9, then it should be 1.8 millimeter. I'm not a fan of that because that means that the really big holes tend to have really huge annular rings, and it's not necessary to do that at all. In fact, my recommendation is based on the standard, the IPC 2221 standard, is I add 0.7 millimeters. That's it. It's as simple as that. So if the hole is 0.5, the annual ring diameter is going to be 1.2 millimeters. If the hole is 1 millimeter, then my annual ring diameter is going to be 1.7. So I add 0.7 millimeters. That's just the way I like to do it. You don't have to do that. You can choose something different. But that's my method. And so you'll find that all of these holes have an appropriately sized annual ring. The exception, though, and it might be glaring here, the exception is some of these really, really giant ones, like this one over here. And the reason is I made this giant hole not for an electrical component. This is actually for a screw. So this is the anchoring hole that we need to use to anchor that PCB to something solid, the actual case. So in that situation, I don't follow that rule. Because there's no electrical connectivity, I'm basically just making sure that the annual ring or annular ring is big enough to cover the actual screw head. So that's a totally different thing. But for most electrical components, 0.7 is what I do. And at the end of that, if I follow those principles, I can then get started in designing the layout of all of my components. Let's go back to our drawing for a moment. We had our logic with our optional interfaces, our optional indicator, and our drivers. The place I want to start with, what we decided to do is our driver is going to be on a separate board, and the rest of this is going to be on a separate board. So I'm going to start with designing the rest of it. The driver will do last. And I wanted to pick the easiest of the bunch. When I was going through the different options, I realized there was a few changes we had to make to the logic so that it will work. And I don't want to get to that today. Today, we're going to start with the easiest one. Let's start with the indicator. And if you remember, the indicator looked like this. It used 3 chips, and those chips were a 4556 chip up front and 2 4555 chips. These are decoders, and it took a 5-bit code. In fact, I think in this case, we only used a 4-bit code, so only 4 of the 5 were used, and those 4 bits were distributed through these decoders, and all these arrows out here went to those indicator LEDs. And this was the equivalent of this in our circuit. So this bottom right half is that indicator. There are those 3 chips, 1, 2, 3, and here are the 16 LEDs and all of the wires that went along with it. We're going to start with this on our PCB. Just before we start laying these LEDs out on the board, I want you to think about the earlier discussion we had about pads and holes and all that sort of thing. If you took the right measurements for the leads that come off the LEDs, you can create the pads in your PCB software. Now, depending on the software that you're using, there's lots of different ways on how to create those different pads. So I won't get into the details on that because they'll differ by different manufacturers or different softwares. There's also handy libraries out there. There's lots of them. So you can go find a library that has pre-built components, which means the pads are already built for you and they're already sized. I'm not a fan of using those libraries, mainly because I find myself checking them anyways, right? And I find that, some libraries come in metric, some libraries come in imperial. I like to work in metric. And so if I have an imperial component, it doesn't quite play right and everything gets misaligned. So I get bothered. I don't know. It's the perfectionist in me. I generally don't like doing that. So I will often create my own components and create my own library. Now, some of you may be thinking, wow, it's an awful lot of work. Yeah, it is. It is. But I enjoy it. Remember, we're doing this because it's something that, well, I'm doing it because it's something that I enjoy. So I like taking the time and creating my own pad layouts and creating my own components and designing them to my own specifications. You don't have to do it. You can go grab a library and start populating your PCB with the stuff you find in the library. Anyways, take a look at this. Here are 16 LEDs that are placed on the board. And you can see each LED is comprised of 2 different pads. Let me zoom in a little bit and we can take a closer look at one of these pads. There we go, zoom in. So these are the pads, and of course they're appropriately sized. This pad in particular, I think actually has a hole shape, a hole of 0.9 millimeters, and it has an entire diameter of 1.6. Remember my specification, add 0.7 to every hole, and that will give you the proper annual ring or annular ring. So that's where these numbers are coming from. And these are sized such that they're spaced perfectly apart so that the LED will slide right in and sit down. Up top here, we see that we have this is a resistor, and that resistor is necessary to make sure that the LEDs light up at an appropriate brightness. The other thing that we have is we have these traces, and you can see this little highlight, this like slight blue line that kind of runs down all of these LEDs. So this is the common connector for that LED. Basically, it means that one prong of all these LEDs are connected. And that's exactly what we had on our circuit board. One end of all the LEDs were connected because the way we've designed it is that the current is going to flow through this point to that prong and down through the common, and that's going to illuminate whichever LED has a positive voltage on it. So that's what this is for, and you can see right at the top, it goes down to the end of this resistor, which then goes to the other end of the resistor, which of course limits the current through those LEDs, and it's going to our power supply over here, or where we're going to connect our power supply over here. The other thing that you noticed, very interestingly, is that the letters are backwards. I've done this on purpose. The board that we're going to put our chips on, I realized that we need the LEDs to show, but I don't want the rest of the board to show. And the LEDs kind of fit very close. They sit quite close to the board. And if I build everything on the same side of the board, because we're using through-hole components, these through-hole components are quite fat. They're thick. And so they're going to take up a lot of space on the board, not just these, but think about like capacitors like these. They're quite tall. In fact, they're taller than the LEDs. So I will not be able to get the LEDs to show out of whatever packaging we use or whatever compartment or container we use because the rest of the components are going to be too tall. So I thought, well, instead of doing it this way, why don't I stick the the LEDs will be on the top and stick the components in the bottom. That way, the components can stick out at the bottom without getting in the way of where these LEDs will be. So the reason you see it backwards on the screen is because the LEDs are going to be plugged in on the other side of the board, not on the front side. And so it's printed in a way so that when you flip the board around, it will show in the right way. And that's also why the resistor you can read it properly because the resistor will exist on this side of the board, not on the other side of the board. So let's start adding some components. I'm going to put in our first decoder. So the first decoder we're going to be putting in is going to run the bottom half of those LEDs. Remember the way we designed our decoders. We needed 2 decoders because each decoder chip, remember, we're using a 2 to 4 decoder, and each chip has 2 of those. So we have the ability to take 3-bit input and give it an 8-bit output. So each decoder chip can run 8 LEDs. So we'll need 2 of them at least. Remember the circuit diagram. If you're interested, take a look back at the circuit diagram. You'll see what I'm talking about. So the first decoder chip we're going to put in, we're going to take those outputs and I'm going to wire it up to these LEDs. Now, how do I know which outputs? The data sheet, of course. And there it is. This is the data sheet for this 4555 decoder that we're putting into our board right now. And if I scroll down into this data sheet, you're going to see all the different pins are highlighted on the data sheet. So I can clearly see of all the 8 outputs, which pins on that actual IC those outputs come out from. So this one says 4, there's 5, 6, 7, and so on and so forth. And so when we go back to our layout, I'll zoom in a little bit so you can see it clearly, we can see our decoder is plugged into the appropriate pins and the lines are going to the appropriate LEDs. Take a look at the first one here. So the indicator 0, that pin is connected to the first LED. The next pin is connected to the next LED, and so on and so forth. As we progress up our LED chain, all of these different pins are connected to that LED. So drawing these traces in your PCB software, the way to do that depends on, well, your PCB software. So, I mean, in this one in particular, it's actually very easy to draw. You'll notice that I try to avoid, where possible, right angles. So anytime there's a trace, I just try to avoid a right angle. I've read in places that it's better for the electronics. I like the aesthetics, actually, of having some of these what we call mitered traces that kind of, glide around wherever you need to go, and make sure that you have enough space between the traces. Your PCB design software has rules built in so that you can run a design check rule to check to make sure that the spaces are adequate and all that. So depending on the way your design software works, there's all sorts of helpers to figure out how this works. But notice the method in which I actually routed these. I actually did this a few times before I got the hang of it. I made a couple of attempts that failed, actually a lot more than a couple of attempts that failed. And eventually I settled on this layout. And I settled on this because I had built the entire circuit in advance, which you're going to see as we move forward. But this point of the story is don't be afraid to make mistakes. Give it a go. Try it. And if it doesn't work, try it again and keep trying, because it takes a while to get the routing right. All these routes are on the same layer. I have not crossed a single route, and I've not used the other layer. Well, except for the common. The common at the bottom is necessary because you can see how these traces cross each other. But because one is green, the green indicates it's on the top layer, and the blue indicates it's on the bottom layer. So that's okay. Perfectly acceptable. These traces actually are not touching at all. They're not connecting. But I can't have a green cross another green, and I can't have a blue cross another blue. That would be bad. So it takes time to kind of get, to get your creativity and artistic and skill level up so that you can start creating like this. And I, by no means, am an expert at PCB design. I've basically just kind of picked this up on my own as I'm doing it. The other thing that I often read about when it comes to PCB design is you really have to take care with how you draw your traces, the length of those traces, whether or not traces are nearby other traces that may have competing signals on it. And all of that is true. However, it only matters when you're working with high frequency circuits. Right now, our circuit is very low frequency for that matter. I mean, it's an LED driver circuit. There's no pulse width modulation here. Everything is going to be running at steady state. There is no high frequency signals in our circuit. And because there's no high frequency signals, all of those considerations for density and spacing and making sure that any sort of cross-talk or capacitive coupling, all of that goes out the window. So it's actually really easy to create a PCB design for non-high frequency circuits. So go for it. Have fun with it. Right? The only consideration we have to be mindful of is the amount of current going through our traces. Right now, we're not pushing any high current. We will later, of course. We're going to get to those the high current LED drivers, which is why we're doing it at the end. But for now, these are just signal traces. So these traces are 0.2 millimeters thick, and they have at least 0.2 millimeters of spacing between them. I think there's actually a little bit more in this case. Let's add our second chip. So here's the decoder 2, same chip as decoder 1. So the output pins are connected. And if I follow the nets, well, not that one. If I follow the nets, you'll see how indicator 8 goes up here, indicator 9, 10, 11, 12. I'm going to have to zoom out now to see the rest of this. There's 13, 14, and 15. All are connected as expected. So both of my decoders are in place. Let's add the next chip. Now we have to put in the third decoder. Now, the reason we had this decoder is not to control the LEDs, but remember, we need to make sure that only one of these decoders is enabled at a time. If you're interested, go back an episode and we can find out the details on how these decoders, the circuits behind these decoders were designed. Today, we're not redesigning a circuit, we're just putting it into the PCB. So I've put in decoder number 0 over here. You can see it over here. And in this case, it was a 4556 decoder. Again, if you're interested as to why we did this, go back and you'll see it in a previous episode. And we've wired in 2 of the enable lines to decoder 1 and the other 2 enable lines to decoder 2. So here's enable 0, meaning when this is active, the bottom 4 bits will be active. When this is active, E1 is active, then the second set of decoders on the first decoder chip will be active. And then the next enable is this one over here, which activates these 4. And the final decoder activates these ones over here. So this decoder chip is in place. Fantastic, and all wired in. So the next one, what I've done is I've basically thrown in a couple of other wires, and I've also added up these little extensions. So what the heck is this? So there's data line 0, and it's connected across all of these decoders appropriately. There's data line 1, data line 2, and data line 3. I haven't connected them to anything yet because those components are going to come later, but I wanted to make sure that they stand out so we can all see where those external connections are going to have to be. Let's add the power and ground. So the power and ground for all of our chips is typically, as far as I'm concerned, I usually do them last. And so the ground lines I often leave to the second layer. It's a habit of mine. And I kind of find that it's a bit of a standard out there. I shouldn't use the word standard, maybe best practices, I don't know. But I've seen a lot of boards do this. They typically put the ground line at the bottom layer, and everything on the bottom layer is often ground, with the exception of some small traces that you just can't route on the top layer. So that's why the ground you see here is in blue. So I've got the ground coming in from our supply. It's connected to our resistor, which will control all the common to the LEDs. And it's going to go down, and you see how it connects to the ground pin for the first decoder. You'll notice that the bottom ground is connected, and it's also connected to these 4 pins. These 4 pins make sure that this decoder is always on. So these are basically the enable pins for decoder 0, and they're all connected to ground, so I wanted to make sure we connect to the ground. Never leave an input pin floating. These 4 pins are the output pins, so we will leave them floating because we're not using that half of the decoder. You'll also notice that my blue lines are not connected. I haven't connected them yet because we still have a few more components to go in. And there they are. So let me zoom in a little bit, and you can see I've put in 3 decoupling capacitors. I need to make sure that these decoupling capacitors are as close as possible to the chips without obviously interrupting any of the traces. So that's why I've kind of put them over here. This top one I'm going to use for decoder 2. This one over here in the middle I'm going to use for decoder 0. And this one that's kind of horizontal I'm going to use for decoder 1. So now that the capacitors are in place, I can attach the ground, which I had left alone. So by putting the ground in place, I've now decided the polarity of these capacitors. So these are going to be the 2 ground pins for these 2 capacitors, and the ground goes onto this side, and then it continues on. So now my ground is fully connected. And if I zoom out and hit the ground layer, you'll see that it's a fully connected ground path going to all of the chips that are necessary. What's left now is to connect the other side of those capacitors. Let's do that now. So I've taken on the top layer this time, you notice that the screen from the 12-volt supply straight down and into the first capacitor, into the decoder number 2, into the second capacitor, into decoder 0, and I've had it split off to this capacitor. Now, I need to get this power signal down to decoder 1, but notice all the green lines, the green traces that are in the way here. I cannot route the power signal to decoder 1 successfully. You know, technically I could. I could actually make it go through some of these pins and kind of meander it through, but I want my power signals to be fat. Remember, the power signals, I can clearly see the difference, which is one of the reasons I keep my power and ground signals fat, or the traces fat. But the other thing is we want to make sure that it's not restricted. I don't want the power supply to these chips to be restricted in any way. So I make it nice and fat. And if I make it fat, I can't squeeze it through these pins. So I'm going to push it down to the bottom layer and run it straight to the pin over here. Now that's okay. Just because I said that I typically want the ground layer to be reserved, or the layer 2 to be reserved for the ground plane or ground wires, that doesn't mean every trace has to be ground. Whenever you need to run a trace down there, go ahead and run the trace down there. And that's what I've done here. So that power signal is now on the layer 2 beneath these signal traces over here. So we're all powered up. Let's take a look at one final thing to this PCB. You notice where these three decoders are. If I zoom in, you may have already seen or taken note of the fact that decoder 0 clearly says 4556, but decoder 1 and decoder 2 don't say anything. I did this deliberately. We know that our circuit says that decoder 1 and decoder 2 should be 4555 chips. But I was thinking about this and I said, well, if I go with that original design, then I'm forced to use two different chips. I have to source a 4555, or two of them, and I have to source a 4556 chip. But the only difference between those chips is the output. So the 4555 chip sends out a high whenever, or a high signal whenever an output is active, whereas the 4556 chip sends out a low signal whenever an output is active. Functionally, they're the same thing. It's just that the output is inverted. So I thought, well, what if I can do something that gives us a little bit of flexibility? What if, instead of forcing the combination of those chips, what if I allowed to use a 4556 chip in place of the 4555 chips? I mean, with, I think, minimal modifications, it should work. And indeed, that's true. So I tried putting 4556 chips, and so therefore the output would be a high. Now, without any further modifications, the circuit's not going to work because it's going to send out a high, and what you're going to get on the indicator LEDs is the exact opposite. You're actually going to get all the LEDs on, but the one that should be lit will be off if you use 4556 chips. But there's an easy way to fix that. If you simply reverse the polarity of those LEDs, then you'll be able to get the circuit to work the way you want it to work. And so I thought, let's build that into this design. So what I did is I added in another resistor up top here. Let's zoom in over here. I added in another resistor, and this other resistor is an optional resistor. So remember before we had this resistor down here where the right side of that resistor is the common, and in that situation, the common would be connected to ground through this resistor, hence that little blue line going down here. But the top side of this, if I connect this through to power, therefore, the common is actually going to be the plus 12 volts, or the high voltage. It's going through a resistor, but it's going to be a high voltage. Then that means I could reverse the polarity of these LEDs so that I can use 4556 decoders instead. And in order to make sure that we can do that, I actually wrote it right on the board. So let me turn off the copper and you can see it. So I've printed it right on the board saying, if we're using 4555 decoders, then use this resistor. If we're using 4556 decoders, then use this resistor. Basically, I've given the person who's going to be putting the chips into this, I've given them an option. If the stock is low or you don't have any chips available, no problem. Just use 4555 chips. It'll still work the same, or 4556 chips, whatever you got available, it'll still work the same. Also, we want to decrease the chip count for our bill of materials. That's always a good thing when designing circuits. So the less variety of chips you can use, generally the cheaper your product. But you do have to change the polarity of the LEDs. And so down here, let me turn off the copper here so you can see it. I've printed I put another text on the board and I said, well, if you're using a 4555 decoder, notice this is reversed because this print is going to go on the other side of the board where you actually put the LEDs in. So that's where I want someone to look at this. So when you're putting the 455 decoders, make sure the anode is on this side and the cathode is on this side. Why I'm using a K for cathode, I don't know. I saw it in a datasheet a while ago, and for some reason, the K just stuck. I know cathode, at least on this side of the world, begins with the letter C. Don't ask me why. It just stuck. It's a habit. I stuck with it. So the cathode is on this side. But if you're using the 4556 chips, then you have to reverse the polarity. So the anode is on this side, and the cathode's on this side. But essentially, that is it for this part of the PCB build. And if I zoom back out again and turn all my layers and my copper layers again, the last thing I needed to do is take this power and route it through that resistor. And I've done that right over here. You can see how I've redirected the power through that high resistor and continued on to the rest of the circuits. So that's basically it. We've completed the first part of this PCB design. There's plenty left to do, and we'll get started on the other parts of it, starting with the next episode. See you then.